All right, thank you for your patience, and then let's start the lecture for today. Today we will learn about the schedulers. And before starting about the scheduler, let me announce something about the grading and then all the other logistics for the class. So right now the canvas shows that there's a total points or something, and then the zone you see is like 100%, and then that does not reflect the weight correctly. So one of the problem of the canvas is that I cannot set the weight. So I need to change all the scoring scheme to reflect the weight. So what I will do is I will create the separate column, and then I will put the raw score directly in there, and also put the letter grade at the end of the term. So please ignore what is said by the Canvas about the total percent that automatically calculated by Canvas. Please ignore that. So I will put the raw, the score based on the 100 points, and then I put that on your gradebook. And then your grading score will be updated tonight, because one of the problem was during the Thanksgiving week, there was a power outage, so that I cannot access the grading machine. So that was one problem, but I will make sure to run the thing tonight, and then you will see the updated score. And then we do not have final exams, so the only remaining thing is all the lab assignment submissions. So these are the last thing to finish. And another thing that I want to announce is I want to lower the grading bracket a little bit, because based on the progress of the students. So we will use this table. So you can easily around -5 or more than that, yeah, for the new score bracket table. Yeah. And then another thing that I want to announce is I would like to accept all your lab submissions until the December 9th without any kind of penalty. So some of the students might upset because that they finished it on time, but that's actually good for you. So you can use plenty of time for just focusing on lab 4. But I want to give some of the opportunity for the students who couldn't finish lab 2 or 3 on time, but still struggling with a lot. And by doing so, that they also can learn a lot of things from the lab 2 and lab 3. And then because that's important, I want to give that kind of opportunity for those students. And then it also applies to all the other students. So for lab 4, if you submit by December 9th, then you will get the full points without any penalty. But another thing is I cannot accept any kind of lab submission after that date, because I have to finalize your grade during the weekend. So please don't ask me about the late submission of the lab after that date. And if you're curious about your potential letter grade, I prepared a not that great UI, but a website that you can connect and then put your raw score. Then you can get what is the weighted score, and then what it will be the average grade. So for the demonstration purpose, I put the 50, 70, 80 for lab 3 and 65 of the lab 4, and then do around 90% on the quiz, then you can get A. And another case of the example is if you finish lab 1, 2, 3 and as a full score, and then if you finish phase 1, 2, 3 as a 90% markish, then you can secure letter grade B. So please use this calculator to estimate how much time you want to put on the remaining lab assignments. And then I hope this would be helpful for you. So any questions before doing recap about the deadlock? Right, and then let's move to next. So before starting about this, you have a question? Yes.
Yeah. So what about for the 544 students?
So
the grading thing works with 544 as well?
So 544, you need to plus 3 for each bracket. And for the calculator, you can choose CS544, then like that will automatically calculate your letter grade based on the grade student bracket. Right, let's do the recap on the deadlock. So we learned about the mutual exclusion and then synchronization using lock, but there could be a case that like the no thread can run through if certain condition called the deadlock happens. So it could happen because it has a mutual exclusion, or it could have hold and wait, or no preemption from the thread that already acquired one of the lock, or it could have a circular wait. So you remember the case of like two threads try to acquire a different lock at the first time, but at the second time, they would like to acquire the lock the other thread have acquired. So in that case, like we cannot proceed anymore. And then we learned about how we can eliminate the deadlock happens per each condition. So if the deadlock happens with the mutual exclusion, then one of the options to resolve it is like the not using the lock. So what that means is that like we use a general lock to control to create a critical section. But in this case, so you can do the same operation. For example, example in the lecture was like adding some of the amount to a shared variable val. And for this one, we can implement that with the lock and then critical section like this. But if we use multiple locks here, then it could create a deadlock. And to avoid that, you can instead use the atomic primitive from the CPU directly. So there is a primitive called the compare exchange. And then, so what we can do instead of like creating the critical section is that first checking it should be val. So this is a typo. First, we read the val first, and then only if that value is the same when we run the compare and swap, yeah, then the exchange will happen. So that actually guarantees that the no other thread gets in between these two operations. So by doing this, we can do the same synchronization operation without creating a critical section using mutex. So this is one of the way to avoid deadlock. But as you see, the critical section is quite general. What that means is that like once you create a critical section with the mutex, no matter what kind of operation you run inside, so that the mutex guarantees the synchronization over multiple threads. But in this case, this compare and swap only works for the adding certain amount to the value. So the implication of one of the caveats of using this kind of transform requires that you need to understand the operations correctly, and then you need to translate the execution operation to this kind of primitives. So what that means is like it's a little complex. So there are several other ways that we can resolve the deadlock. And then all these four, the mutual exclusion, hold and wait, and then no preemption, and then circular wait. These are not independent at all. Yeah. And then there are several ways to resolve that. And then some other way to resolve the deadlock causing by mutex is that if there are two or more locks to be acquired by a thread, then depending on the lock acquisition sequence, so acquiring lock from set A first, then B, and then if the other thread try to acquire set B first and then A, then there could be a deadlock. So to avoid that, we can introduce another lock called the meta lock. So we can create another critical section for just acquiring the lock. And then that guarantees that in acquiring these kind of the multiple locks, there will be only one thread will be involved. So that's guaranteed by this outer critical section. So that's the way to avoid that. So to create the data as a thread safe the data structure, we learned about that like we can have a meta lock like this. So even if we order the lock acquiring sequence like this, if the arguments order switch it, then that could create a deadlock. So we can avoid the deadlock in this case with the meta lock. And then similar case can be avoided by having a trilock. And the concept of the trilock is that suppose there are two locks to acquire, A and then B. So in case if a thread can acquire lock A, but they fail to acquire lock B, so in this case, instead of like holding lock A before acquiring lock B, release lock A and then let others have the chance to acquire both of locks. So not like acquiring lock A and lock B, it's more likely acquire lock A. And then if you fail to acquire lock B, then release it and go back. And then that will remove the deadlock condition about like the having a circular wait kind of thing. And then the circular wait condition is that there are two or more thread try to acquire two or more locks, and then each acquire the one of the lock, and then try to acquire the lock acquired by other thread, so that would cause a circular wait. And then the simplest case of the circular wait is like when we have two locks and then threads are acquiring in a different order. And one of the ways like if you use these kind of locks as a global variable, then there is no way that the L2 and L1 get swapped out. Then you can safely use this kind of implementation. But we have seen that from the thread safe data structure example. So function argument can be switched. So even if you ordered all the log acquire correctly, then that could be mixed. So in that case, you need to have like the unique identifier for each lock, and then you can order that. And in the computer programs that use virtual memory space, we naturally have the address of the variable as a unique identifier because virtual address is unique to one process. Yeah. So because the lock variables are pointer, so based on the address, we can order that and always having a same order across the multiple thread for acquiring a lock. So that would remove the deadlock. And then these are the recap about the deadlock. And any questions about deadlock for their conditions and then how to resolve that? Right, then let's move to the scheduler part. So in lab 3 and lab 4, actually in lab 4, I believe, yeah, we implement a very naive scheduler that goes round robin, and then if we found one of the environment and just run it, yeah. And that's a very simple scheduler. And the scheduler in general is an algorithm that decides which process or environment need to execute as next. Yeah. So there are several ways that the programs surrender their execution right. So for example, operating system invokes one of the program, and then they runs. And then in the non-preemptive systems, what we need to do is like we need to ask the program to call yield to surrender their execution right to the operating system. Then operating system take care of it and then run their own algorithm to schedule out that program and then schedule the new program. But in case of the preemptive multitasking, any kind of the hardware interrupt, for example, if we receive some of the keystroke or some of the data from disk ready, or some of the buffer on the network card is full, then the CPU will generate the hardware interrupt. Then the CPU will stop whatever they are running and then store the frame for them and then run the process their hardware interrupt and then go back. And then when they are getting back to the user level program execution, so the one way is going back to the program that we were running. Or we can also switch the context to the another program to give the chance to the another program to run. And the reason why we need scheduler is, so CPU is a limited resource. And then we need to have a CPU to execute the code and process data. And then, so nowadays, like you have laptop with the dual core, quad core, octa core, but usually your operating system runs more than 300 processes, like for system management and all the others. So this is the one of the example screen in my laptop that I use for development. And I can easily see like the many processes are running. And my laptop is only has 4 cores. So the 4 CPU cores need to be allocated fairly to all these programs, to make them run robustly. So the goal of the scheduler is that, so the problem is that we have 300, 400, 1000 processes are waiting, and then we only have 4 or 8 cores. And it's about how we schedule those programs to maximize the efficiency or maximize the fairness, something like that. So based on our purpose of the job, so we can edit the scheduler to fit the scheduler algorithm to perform better based on that for the target purpose. So we will learn about like what kind of scheduler algorithms are there, and then what are the effects of each of them. We will start about that. So even if in the multi-core era, we don't have like a number of the CPU cores available for the number of the processes, we need to run multiple processes in a single CPU simultaneously. So easily, if we divide it like 300 by 4, then like we need to run around like the 70, 80-ish processes per each CPU. Yeah, so that's happening. And then we already run that in the preemptive multitasking with the help of the timer interrupt. So usually in the operating system, it comes with the 1 millisecond window. So theoretically, with that configuration, in 1 second, we will have a 1000 chance to switch the process for one single CPU. And then the scheduling is all about like how we use those kind of the opportunity, and then how we distribute those opportunity to the processes to maximize the system's performance. And then let me tell you about like one of the case that we can increase the system's efficiency with the scheduling. And then take a look at the case about the Nginx web server. So the Nginx is just a web server. So our course website is running with the Nginx. And then suppose one of the students connect to my course website, then the server for Nginx need to serve that. And then while handling the client execution, they need to receive like what kind of request coming from the internet. And then usually internet latencies are like the 10 or 30 millisecond, which is much bigger than like the time window, interrupt window of the CPU. So what happens if we run the Nginx without any kind of preemption? So there is a job, and then there's a certain point that we need to wait for the client's input from the internet. And then in that case, we let the CPU do nothing, and then just wait. And then whenever the network packet comes in and that's available, then we can continue the job. But so we can easily see that for this red block. So you can think like this x-axis as an increasing time. So we need to wait around. So for the network packet delay, they are having around the 10 to 30 millisecond. And then for the 10 to 30 millisecond, we need to wait. and then our CPU cannot do anything. So that's waste of time. So they're one of the easy intuition heuristics that increase the system's performance is that while a program waiting for the IO or another jobs to finish, then we can actually run the total different job on the CPU. Then that actually not wasting CPU cycles, and then everybody will be happy. So that's the job of the scheduler. So whenever they detected this kind of the wait, then they can schedule some independent job to increase the system's throughput, and then not letting the CPUs idle, that kind of thing. Yeah. So if we have a good scheduler, then like we could have a better CPU utilization. So as I told you before, the scheduler is just an algorithm. So simply, it chooses which process to run as next. That's it. And then this kind of a scheduler runs when interrupt happens. So the interrupt means that like we need to interact with the hardware, or we need to wait for some of the operations for other than the CPU or something. Then we stop it there and then try to schedule another process to have a better utilization of the CPU. Or if we want to have fairness, for example, all the process will have like a 1 millisecond execution right. And then like it will be fairly given by one each. So that we can do that. And then in the preemptive multitasking system, whenever the timer interrupt happens, we can switch the process to share the CPU as a time sharing manner. Or whenever you create a new job, then if there are thousands of the processes are running, your new job cannot be scheduled promptly. So in that case, some of the systems are optimized the responsiveness by like scheduling the recently executed program first. So there are many reasons that we need to have schedulers. And then the important concept here is that there are two types of the schedulers. One is the non-preemptive and the other is preemptive. So for the non-preemptive systems, do you remember the picture that I presented Dodge with the much waiting with the if one of the program runs a while one or something? So in non-preemptive system, there's no way the operating system stop the user level execution. So schedulers need to wait until the program voluntarily surrender their execution right with the sysyield kind of the function. Yeah. Or whenever there's a system call invoked by the user program, then the operating system automatically gets the execution right. Then we can run the scheduler up there. So that means we need to wait until if there's a system call or if there's a yield system call from the program. So there always could be a chance that the one program does nothing and just in a while loop, never surrender, don't call system call. Yeah, then yeah, that could run forever. So that's bad for the schedulers. So even if we have a good algorithm, we cannot run it if the target program does not surrender the execution right at all. So that's basically why most of the modern operating systems for the general purpose, for example, Microsoft Windows, Mac OS, Linux, they are all in preemptive execution mode. And then in the preemptive systems, operating system will always take back the execution right with certain time window or any kind of the other hardware interrupts. So we can configure it more responsive. And then we can, if we allow 1 millisecond per each process, then that could be more fair per each process. So we just briefly learn about what's the scheduler. And then next is about the goal of the scheduler. So I just introduced that we can maximize the CPU utilization by if the one of the program waits for the IO, then we can schedule the another one in the meantime for running that. So that's the one of the goal. And there could be some other goals based on the purpose of your operating system. So Right now, some of the students may think that the operating system as a general one, like a Mac OS, Linux, those kind of thing. But in the embedded systems or like the systems with the systems that is used for the manufacturing or infrastructure, those kind of the low-end systems, they do not have like the super fast CPU to run all the complex features of the operating system. So instead of doing that, they try to minimize their operating system size and then just include the required part without all the rest of the part, and then try to customize their operating system to optimize to certain purpose. So that could be maximize the number of the jobs finished in certain time window. So for example, within 1 minute, how many of jobs you can retire. Or you can optimize the operating systems to have a more responsive execution. So what that means is that like there could be many jobs, and then we will measure the job start and finish time. And then we can also measure the average job finish time. And then that's the time that if suppose we are running a server program, and then that's the actually latency of each user. Yeah. So that we can measure that, and then we can optimize, we can build a scheduler to optimize that. So the important thing here is that there could be some of the general algorithms, but there are some specialized algorithms for a specific purpose. Yeah. So depending on the system's requirement, depending on the goal of the system, we need to wisely decide about like what kind of the scheduling algorithm to use. And then let's go over some of the examples of the scheduler. And then let's take a look at how it affects on the effectiveness of the operating systems. So the first scheduler that I would like to introduce is like the very simple one, first in, first out, FIFO scheduler. So based on its name says, it's just a first in, first out. So schedule jobs based on their arrival time as a priority. So you can think that all the horizontal line as a time. And then suppose one of the job one, arrives at this time. And then suppose there is no process that we are running for now, then we can schedule job one whenever they arrives. And then a few milliseconds later, job two arrives, but we cannot schedule job two. Suppose we only have one CPU, then we need to wait until job one finishes. The definition of the first in, first out is that before the first coming job retires, we cannot schedule the second one. And then there could be a case that the job three could arrive in the meantime of running the job one. And then we cannot schedule these two jobs until job one finishes. And then if that finishes, we can schedule job two because job two arrives ahead of time than the job three. And then after job two finishes, then job three can be scheduled. So this is how we can schedule as like the FIFO scheduler. Yeah. So it's not about the primitive execution at all. So we will just let the program run and then wait until it finishes and then schedule next and schedule next. So you can think it as like with the very with the real world scenarios, such as like the grocery cashier line or a drive-through. So for these kind of cases, so you need to wait until the person in front of you finishes their transaction, right? So that's basically the FIFO scheduler. So it looks very simple, but it has some of the advantage. So let's take a look at the pros and cons about the FIFO scheduler. So the pros is that it's very fair. If you want to get your job scheduled, come earlier. Yeah, that's it. Yeah. But the problem is, so its average wait time could be longer And then it could be shorter with the different scheduling algorithm. Yeah. And then let's take a look at the example. Suppose we have 5 jobs like this. And then job 1 and 2 has the job duration as a 10 seconds. And then job 3, 4, and 5 has a job duration as a 2 seconds. And then suppose all the jobs arrives as a sequence as a job 1, 2, 3, 4, 5. Then based on the FIFO scheduler, we need to run job 1 first. After 10 seconds, we can schedule job 2. And then after 10 seconds, we can schedule job 3 and 4 and 5. That's good. And then let's measure the wait time of each job. Suppose all the jobs coming at the 0 second for the job 1, 0.1 second for job 2, 0.2 for job 3. So yeah, something like that. So in that case, job 1 did not wait and then just scheduled. Job 2 waited 10 seconds. Job 3 waited 20 seconds, 22, 24 seconds. So after writing down all the wait time of each job, and then we can average out. So in this scheduling method, the average wait time of each job is 15.2 seconds. Then let's schedule it in a different way. So suppose the job arrival sequence was a 3, 4, 5, 1, 2. Then our execution would be something like this. Schedule 3 first, and then 4 and 5, and then 1 and 2. Then let's measure about the average wait time. So job 3 waited 0 seconds, 4 waited 2 seconds, job 5 waited 4 seconds, and then 6 and 16. So you will see the numbers definitely smaller than before. So 5.6 seconds for the average wait time. So I just changed the scheduling order, and then the system's average wait time could be drastically changed. So this is a special case. So that's why it works with the scheduling all the shorter job first for this kind of purpose. So depending on the system's goal. So if your system's goal is all about the fairness, then it's good for using FIFO scheduler. But if that is not the case, that if you want to maximize your throughput, number of job retires, or minimize the latency of the client, then the better to think about using the different scheduling algorithm. So the next scheduling algorithm that I would like to introduce is doing exactly like this. So FIFO was first in, first out. And then the next algorithm is called SJF, shortest job first. So we actually schedule all the shortest job first, and then longest job later, right? And then the shortest job first is for the non-preemptive version, because we cannot stop during the program's execution. So schedule it like this. And then there is a preemptive version of the SJF, and then that is called the shortest remaining job first. And then you can think about what is the difference between the preemptive and non-preemptive execution is that. So for the non-preemptive execution, we will wait until each job will be finished. But in the preemptive execution, we will schedule in the order of a remaining job time, but we will give only one slice of the execution right to each execution. So what that means is that in this case, if job 1 got scheduled, in non-preemptive case, we wait until job 1 finishes 10 seconds. But in the preemptive manner, after running 1 second, we can forfeit the execution right and then schedule another one. Then job 1 becomes the remaining time as 9. Yeah. So that by reducing that kind of remaining time, and then we can apply this kind of the shortest job first algorithm to the non-preemptive machines, preemptive machines. So we already see the example of the shortest job first, and then the contrasting between to compare the FIFO and then shortest job first scheduling. The noticeable difference is that their average wait time, the latency to get the result, could be shorter. Yeah. But can you guess any kind of problem of the shortest job first scheduling? Yes. That's right. That's called as a starvation. So we need to feed each process with the CPU time, but that could be a case that the CPU time all goes to the short job, and then longer job cannot have the CPU time at all. So that's the one of the problem. And then before getting to there's another problem. So in this case, so we assume that we know all about what is the expected running time of each job. But in reality, we cannot measure what will be the expected running time exactly. Yeah. So even if we have made a conjecture for like job one would run for 10 seconds, it could require 12 seconds, or it could be finished in 8 seconds or something. Yeah. So to maximize, optimize with this kind of the scheduler, we need to know about the job finish time precisely. Yeah. But in reality, we don't know what is the exact job finish time. Yeah, there could be some of the time window for like the at minimum, it takes 3 seconds, or at maximum 7 seconds. We can have that kind of range, but there are many cases that we cannot have an exact job running time. And to resolve that, one of the ways that we can let the program change their expected running time while they are running. But in that case, there could be a case that the one process comes in saying that they are just a 1 second job. And then right before finishing 1 second, try to extend that. And then that's another 1 second job scheduled, extend that again and again. Yeah. So that is related to the starvation case. So let's take a look at that. So suppose I have a job that takes 10 seconds. And then before, so I submitted the job, and then before that was scheduled by the operating system, suppose 100 of like the 1 second job comes in. Yeah. Then our scheduler will work like this. Yeah. And then after waiting 99 seconds, then now job one is expecting that, oh, next is my chance. But there could be a case that another 100 of the 1 second job comes in again. Then job one can never be scheduled. Then that kind of case is called a starvation. So once there could be a case that the process cannot get the CPU execution slice at all. Yeah. And then there is a matching counterpart in the real world for this case too. So when you go to the amusement park, there's a regular entrance, and then there's a priority entrance, and then right before your turn, if all the people comes through the fast pass or something, then you need to wait indefinitely. Yeah. So that could happen in the shortest job first kind of the scheduler. And then that kind of thing can always happen if we set a certain priority for the scheduling. So in shortest job first, we set the priority as a job length. So the shorter one has a higher priority. And then there could be many cases that we can set the priority. For example, if the program runs with the user interaction UI, then we need to make it more responsive to the user. In that case, we need to give the higher priority than like if we have some of the background job updating the time. and then that runs like the once every 6 hours or something. In that case, we don't need to schedule that often. So we can reduce the priority like that. But the same kind of the starvation happens if the high priority job keep comes in, then there could be a case that your job cannot be scheduled at all. And then these are the non-preemptive version of the schedulers. And for the preemptive systems, so something similar to FIFO, which is fair, is called round robin. So the difference between the non-preemptive and the preemptive system is that like for the preemptive system, you cannot run the program quite along without interruption. So even if there's no hardware interaction at all, you will get timer interrupt. And then that actually stops the program and then give the another program to get scheduled. Yeah. And then how round robin could work is, suppose we have these kind of the 5 jobs, the same case of the FIFO and SJF. And then if we implement the round robin scheduler on the preemptive execution machine operating system, then how it runs is, so suppose the job was coming as a 1, 2, 3, 4, 5, then schedule the job according to its arrival sequence. And then in this case, just run one time quantum per each. And then if we give that kind of the one quantum for each of the processes, then roll back, and then give it again and again. Then after receiving 2 time quantums, these jobs will be retiring, and then we will let the other jobs to finish. So the next is about the pros and cons. So good thing about this kind of scheduling is like it's quite fair. So whenever the timer interrupt comes in, it gives the chance to run about the program one by one. And then if you wait there, and then you will eventually get the one-time quantum slot if it goes all over the processes. And then it's fair. And then another benefit is like if there's no starvation. So if you wait for a long time, then round robin go over, and then it rolls back, then it will give the running quantum for you. Okay. But the problem is that, so when we run job 1 and then try to switch to job 2, what happens internally? So we have already seen that in JOS. So think about whenever the system call or that kind of the interrupt happens. So the process runs, then if that kind of the interrupt happens, then it needs to store the trap frame and goes to the operating system's trap handler, and then run all those kind of code, and then switch the context with the changing CR3, and also like the schedule the process and then get back. So between this job 1 and job 2 execution, so switching the context between the processes are not free. So we need to consume the certain amount of the CPU cycles to do that. So the bad thing about the round robin scheduling is like it would involve a lot of context switching. So in the non-preemptive mode, for running these 5 jobs, we only need 4 context switch. 1 to 2, 2 to 3, and then 5, right? But in this case, we need to have a lot of context switch based on the job running time, so that is the overhead for round robin. So the summary of like a simple schedulers, FIFO is first come, first out, non-preemptive. So we need to wait until each job need to be finished. And then in that case, if we use FIFO, the good thing is that's fair. But the problem is like it's not responsive because like the job 5 should wait a long time, and also like it will have a higher average wait time. And then there is an algorithm called the shortest job first. Then it will have low average wait time. That's good. But the problem is like that it's quite unfair. All the shorter jobs scheduled first, so the longer job could wait indefinitely. And then in the preemptive system, we could do FIFO in a similar way, but because we need to run like a one-time quantum slot and then go back again and again, so it will be a round robin. And then good thing about this is like this is very fair, and then it also does not involve any kind of starvation. If you wait, then you will get the time slot. But the problem is like it will have high average wait time because shorter jobs are waiting in here, yeah, but not that high like FIFO, yeah. But it will involve a lot of context switch overhead. Any questions about these basic schedulers? Yes. So we can do that, yeah. And then like right next slide is about describing the prior scheduling with aging. And then that's actually we decrease the priority and then to manage like to not having starvation, even if we have a priority scheduling. So starvation happens because we honor priority. And then if the high priority jobs keep coming, then like we suffer starvation. And then one of the way to remove that is give the reward to the processes that are waiting in the queue. So for example, processes can start with the priority 1. And then if they wait about like 10 seconds or something, then we can increase the priority so that there's a way to, like avoiding starvation like that. Yeah. All right. So the next is about the priority scheduling. So the priority scheduling is a general case of the SJF. Yeah. Then actually the general case of like the FIFO scheduling too, because in FIFO, the priority is the job schedule time, right? When the job was committed to the scheduler, right? That's the priority. And then SJF, the job finish time is the priority. But in the priority scheduling, it generalized the priority so you can set any kind of value as a priority. Yeah. And then what it will do is based on the priority number, the scheduling algorithm will determine which job need to schedule as a next. Yeah. And then the use of like this kind of the priority scheduling is something like for the responsive programs, some of the, for example, if you're running a Tesla vehicle and then the visual sensor need to be very responsive to detect any kind of the abruptly changing environment or something. So in that case, you want to set a very high priority for that kind of process, while like having a very low priority for like playing the music or something that's some of the passive job for the vehicle. Yeah. And then you can think it as like the SJF is one of the priority scheduling mechanism, and then priority is based on the job finish time. And then you can think of the entire priority scheduling as a generalized version of the SJF. And then let's take a look at the example of the priority scheduling. So in this example, we have 2 numbers in each job. And then the first number in the tuple is the job length. And then second number in the tuple is the priority. And then in this example, low number of the priority means that higher priority. So 0 is the highest priority, 0, 1, 2, 3, 4. That's how the priority, so higher priority counted. So if the priority sets like this, then the scheduler will choose priority 1 first. That's job 4. Next as a priority 2. Next is priority 3, 4, and 5. Yeah. And then this is how the priority scheduling can run. Yeah. So that's strictly based on the priority. But in this kind of the priority scheduling, we already know that the SGIF suffers starvation. And then same thing could happen in this case. If you have a priority 4 job here, and then you have a priority 1 jobs, many of them, then it will run like this. And then before finishing these 2, if we have another, the priority 1 job comes in, then this process cannot be scheduled. And then one of the way to avoid this kind of the starvation in the priority scheduling is so-called aging. So it's more likely giving reward to the processes that cannot get the schedule for like a certain moment or certain time window. So one of the way to do that is we can increase the priority for the processes that has been waited for a long time in the scheduling queue. And then we can decrease priority if the one of the processes got recently scheduled and then run the CPU time. So it's something like punish recently executed processes and then promote the long-waited processes to make it fair. And then let's take a look at how this kind of the priority scheduling can work with the example. This diagram is a little complex, but let me explain in a good way. So suppose we have these 3 jobs. So job time 3, priority 1, job time 3, priority 1, and then job time 10 and priority 4. And then based on the priority scheduling, we should schedule this one first. The same priority, but suppose this one comes first. Then we schedule this one first. And then after running this one, because we already consumed the 1 time quantum, so decrease the expected remaining running time from 3 to 2, and then increase the priority number, actually the decreasing the priority of this one. And at the same time, what we will do is for the processes that were waiting in the queue, we will give the reward to them. So what we will do is just decrease the priority to give the higher chance to get scheduled in the next time for each of the processes. So previously, the job length 10 job was priority 4, and then it could be 3. But if we set the priority 1 as a minimum, then we cannot increase the priority for that. So punish the recently executed process and then give the reward to the weighted processes. And then priority 1 is the highest one, so we cannot change that anymore. And then if that happens, then this process becomes priority 2. So the next process we need to schedule is the priority 1. Then it will, so the longer job was waiting there. So it became 4 to 3 right after running this. Then right after running this, it'll be 3 to 2. And then next, we will have these 2, and then the gray job, because it has increased priority number because it has executed 1 time, but at this time, this one has not been executed. So in that case, it will have the reward to increase the priority for that. Yeah. So that's how it works. Then it will be fairly scheduled, and then eventually the waiting job becomes 0. Then that can be scheduled as a 4th time for the time quantum, and then it will run for just 1 time quantum and then change it as a 9,2 job. So 9 is the remaining time, and then priority number will be increased by 2 to get the lower priority than that. So this kind of by applying this kind of the way, then if one of the process wait for a long time, they will be at the highest priority. So they will definitely be scheduled. And then if the sum of the process scheduled too frequently, then they will have a penalty and then they should wait. So that's how we can control about the priority scheduling and then not to have starvation. And then this is just a simple aging method. It's just a simple one. And then actual scheduling algorithm could be much more difficult, complex about that. Any question about the priority scheduling with aging to avoid the starvation? So conceptually, it's not that complex and difficult. Is there a question? Yeah. So it's something like giving reward for those who waited, and then punishment for those who just run it. Yeah. And then in the operating system, so we are using this kind of priority scheduling, and then scheduling algorithm could be complex, but we cannot make it too complex. The reason is I mentioned about there's an overhead between the context switch from the one process to the other. And then in our modern operating systems, that happens at least once in 1 millisecond. And then suppose your scheduling algorithm takes more than 1 millisecond. Then to run the 1 millisecond of the program, we need to run more than 1 millisecond for just scheduling. So that's total waste of the time for the CPU for not doing the job and then do the scheduling job. So that we cannot make the scheduler to be like indefinitely taking long time or too complex. So the one of the thing that could make you feel about like the scheduling algorithm need to be simple is that the Linux has the O1 scheduling algorithm. And then what that means is that their execution time for the scheduler will never change depending on the number of the processes. Yeah. Because the efficiency is so important. So the Linux decided in that kind of decision. So even if you have 1 million processes running on your operating system, their scheduling algorithm will not take running too long. Yeah. So that's the design. But if we design like the scheduler algorithm as an ON, then the scheduling time will go up. Yeah, if we have many processes around the system. So in that case, like you will see that the system will be eventually slowed down, and then like their throughput will be worse than the others kind of systems. And then we are using the priority scheduling in practice. And then let's take a look at the step diagram. Here it is. So here, this column is all about the process ID, and then this column is all about the program name, and then this is about the username, and then this row, 20, 19, or some of these. Yeah, these are indicating the priority. So in Linux, priority 20 is the lowest priority, so normal priority. And then anything that has a value lower than this one. 19 has a higher priority than 20. And then minus 20 has the highest priority in Linux. And then take a look at that. So all the other normal programs are scheduled with the priority 20, but you will see that one of the processes set as like a priority 19. So more higher priority than others. And then let's take a look at that. What is that? And then it's about libsystemd journal D. And then what journal D does is like it's journal daemon. And then what it does is like it manages the file system. And then running in the background whenever there's a file system transactions, and then it does the background job for that. And then that need to be very responsive to support the other programs disk operation. Yeah. So to be more responsive, yeah, the Linux operating system, so especially for Ubuntu, yeah, they set it this daemon runs with the higher priority than the other applications. That's the one of the example. And then that's so-called a nice value. So my slide is wrong. So 19 is the lowest priority. No, 20 is the lowest one, as we've seen in the HTOP program. And then in Windows, if you open the task manager and then get the advanced menu, and then from the process list, you can see that the base priority, then you can also change that by clicking right and then setting the option for that. So in Windows, if you just run the program, it always run with the normal priority, but you can change it to make it more responsive. Then you can have like the above normal high real time, or if you want to make it as a not responsive, but not that frequently scheduled, then you can set it as a low. And then one of the things that you can test, you can do the test is like, suppose your laptop is 4-core machine, then write a program that does while one, and then run 4 instances of them. And then that will slow down your system a little bit, but you can still move the mouse and then run another programs, and that's okay. But if you set all those while one program, 4 of them, as a real-time priority, then you will see the difference. Yeah, you will see that the CPUs are more goes to that kind of the meaningless while job. Yeah, and then while not accepting your inputs. Yeah, so to feel about like the starvation, or it's not a starvation, it's just to getting the delay for like the scheduling. Yeah, so that you can play with the schedulers with that. All right, any questions about the lecture today? So actually, the scheduling is very important and then affect a lot to the entire system's performance. Yeah, and then like so the one of the unfortunate thing is like that I want to get into more about the scheduler, but within the 10 weeks of the schedule, so I cannot do that. But if you are interested in learning more about the schedulers and then other concurrency in the operating systems, feel free to send me a message or email message. Yeah, then I can introduce some of the things that you can read and study about that. All right, if there's no other questions, let's finish lecture here. And then for the lecture on Thursday, so what I will do is like I will do the recap about the entire class. And on top of that, I would like to introduce some of the state-of-the-art technologies in operating systems. So for example, we learned about the process as an isolation mechanism. So in that case, operating system can see whatever user program runs. But that could be problematic if you think about some of the cloud machine case. So for example, suppose you are using the AWS cloud and then running a user level application on there. And then suppose you are processing some of the secret data in there. But based on the system design, operating system can read anything of the processes, and then the virtual machine monitor can read anything about the operating system and the user process. Then what that means is that suppose you are renting the Amazon cloud and then storing your photos on that. Then even if all the connections are encrypted, Amazon, yeah, they can naturally see all the content. Yeah. So there is a so-called new term called the confidential computing. So there is a way to have the isolation between the operating system and the process, and also for the virtual machine monitor to the operating system. So it's something like, even if Amazon owned the entire computer, and then they have a full privilege to the machine, they cannot see some contents of the processed by the tenants. So that there are techniques, something like that, and then I would like to introduce some of the those new techniques in the operating systems, because we just learned all the old textbook stuff during 10 weeks. So that I would like to deliver some more fun things at the end. Yeah. All right. And then there's one question from online side. The question was if we have finished everything prior left 4 with 100%, then we would be guaranteed at least a B. That's correct for the CS444 students. So like I intentionally changed the grading bracket to give the B grade to those who finish it quiz well and also finish lab 1 and 2 and 3. Yeah. So before finishing the lecture today, is there any other question last minute? All right, and then if you have further questions, then please come down here or like send me a message via Discord. Yeah. Thank you.